welcome everybody to this webinar. Thanks for participating. My name is Germán Regal. I'm Associate Director of ITS, and it is a real pleasure for me to conduct this webinar. As you know, we are celebrating today the official inauguration of our center, which is the ITS Basque Center for Language Technology, which ITS in Basque means a word. So this is the Word Center. For us, it's a great day. We start a new journey. I think we hope with all of you also. And we are very grateful to Eduard, who accepted our invitation for this event. Ed Hovy, which is the invited speaker today. Even his short CV is very long, so I will try to do it as fast as possible, but I think also I will give you some light about himself. So Eduard Hovy is professor now at the Language Technologies Institute in Carnegie Mellon University in Pittsburgh. He also holds adjunct partnership in CMU's Machine Learning Department and also in the University of South California in Los Angeles. He is a PhD in artificial intelligence at Yale a few time ago. He's also honorary doctorate from several universities, including UNED, which is the Universidad Nacional de Educación a Distancia in Spain, and also the University of Antwerp. He is also founding member of ACL, so with the Association for Computational Linguistics, which is the main association of computational linguistics in the world. His research focuses on computational semantics mainly, and also machine reading, comprehension in text, information extraction, text summarization, question answering, building large lexicons and ontologies, and machine translation. So almost all the area. He has been working in many things. Now currently has around more than 40,000 citations in Google, so this is quite prominent, an important contribution to the scientific world. In more than 400 technical papers, so it's a quite important person in the area. So he was also as president of the ACL in 2001, and he's a reviewer and advisory board in research institutes and funding organizations in Germany, Italy, Netherlands, Ireland, Singapore, and United States, and many more things. And that's why it's a real pleasure and an honor for us that Ed Hovy has accepted this invitation, because he's also very busy. So thanks once more, Ed. And I think now it's your turn, what all these people here is waiting for. So thanks again.
Okay, thank you, Germán and Eneko. Thank you for that warm introduction, and good afternoon, everybody. And I would like to say it is an honor and a pleasure to be here at this occasion, virtually, if not in person, because it's such a great, important thing when a new center starts, a new center like this. While you were talking, I was thinking, you know, almost half, it's probably safe to say that more than half the people in the world alive today have used some kind of language technology, whether it's a speech system that understands their speech or corrects their speech, or whether it's a machine translation system, or whether it's Google or something like that. Almost anybody who has touched a computer has used this technology somewhere. And if you think how many people in the 60 years of this field have actually worked on language technology, my estimation is it's less than 50,000 people. Now, how many people in the world do you think have made motor cars possible, or made electricity possible, or something that a large proportion of the world has touched. It's thousands, hundreds of thousands of people who went into making cars and making electricity systems and making whatever it is we use. We are a very small group of people who, through hard work and energy and love for the field and intelligence, focus together to create something new, and we're constantly trying to create new services and new capabilities that make computers able to work with language and increasingly to work with knowledge and increasingly to work with intelligence. Language is a great window into what intelligence is all about. So it's wonderful to see a new center happen, a new center come about with such good people and such talent and such energy to actually make and focus more effort more effectively. So I'm really excited. I really am happy to be able to be here today. So I would like to share now a few thoughts with you on my slides here. Can you see them? Is okay? Yeah?
Yep.
Okay. Thank you. All right, so I called it the birth of a new center, making the most of a newborn technology. And the theme here is changes, what things change and what things don't change. But I want to start first saying the Basque Country and Spain can be proud of its NLP. From the earliest years, NLP has been very strong in Spain compared to, or in Spanish, Spain and Basque Country compared to other countries. You know, Germany, of course, Italy, of course, England, of course, Holland to some degree, but many other countries took a long time to get enough people to start doing notable NLP. Spain has done from the beginning, thanks to Felisa Bedejo, who was in Donostia for a while, and others. So for a long time now, there have been NL conferences, for instance, and there's been sophisticated research in, for instance, Donostia and Madrid and Barcelona and many other places, and support for international evaluation campaigns and research centers and teaching and summer schools and all kinds of activities. Every year there is something happening. Spain, of course, is popular for tourism, but of course popular for major conferences because it is a nice place to go. There are pinchos and other very nice food and things, but there's also very interesting intellectually and a nice environment, friendly and stimulating. And then, of course, as Eneko was showing, there's a consistent presence in international funding, which reflects the power of the work inside Spain. So it is good and natural and correct that there be a center like this, that there be multiple centers as there already are, and that Donostia and now the HITS Center has its place in this ecosystem here. It's so nice to be here when it opens formally. So I then started thinking, you know, what is HITS likely to do in the next few years and over its lifetime? How can you guess? How can you advise? What would you say? So I thought, if you could fast forward and look over the decades, what would you see how NLP, natural language processing, grew? And where is it going now? And now in our new era, the last 5 years, we've had these deep neural networks, and they have revolutionized a lot of things, including NLP. And where do we go with this? Because we really don't understand how they work. So if you look over the history of NLP and you look at those change points, the major new ideas that made things move in a big step forward, and you look at the pattern there, then maybe you can get a hint of how you can best employ the forces that are concentrated at HITS to be on the forefront of making new significant changes, not just little changes. So that's what this talk is all about. So I would like to talk about changes that make a difference and changes that don't. All right. So first, I would like to describe what is NLP and what sort of the essential changes versus the incidental, the nice changes, but not the important ones. And then where are we now going and how does this mean for HITS? What does this mean at the end a little bit? So let's begin here with the core NLP pipeline. This isn't completely accurate, but it gives a sense of all the things you do. In comes a speech wave, somebody speaks, and you do speech recognition, and then you have a series of words, and you do parsing, and then you have a syntactic parse tree, and then you do natural language understanding or semantic interpretation. You have some kind of a frame structure that pulls out the semantic pieces and makes them in a regular representation, maybe linking to an ontology, and then you do some stuff, and there's all the internal things that you would like to do: question answering and machine translation and text summarization and dialogue and voice and stuff. So sometimes you shortcut here and you jump over some of these stages, but if you make a map, these are all major stages that people tend to do in the field. Going out again, you sort of have to do content selection, macro planning it's called, and then you can do sentence realization and you get a string of words, and you can do speech synthesis and get a speech wave coming out. If you do the whole thing, you get a dialogue system. Maybe some parts you just get some pieces, you get a question answering system or a summarization system or information extraction. You have to do lots of smaller steps there, which are all technical names, and you have to use things like dictionaries and grammars and in different languages and stuff. So there's a lot of work. You have to put together a lot of pieces. It's a complicated machine to make a language technology engine work. And it is not obvious when you look at it from the beginning, or when you listen to philosophers or linguists, exactly what you need to do. So it has been a journey of 60 years for us to realize what are the powerful techniques that we can use, and what are the sort of useful ones but not so powerful, and how do we move ourselves into the next new powerful capability. So if you look at some applications, I chose 4 to give just a little history of them, and I'm going to concentrate on them in the next few slides. Let's look at the problem. When did the work start? What kinds of solutions were brought about? How did we measure the progress? Because this is an engineering field, we look for progress. What kinds of competitions were there that apply the measures and tell people what is the best thing to try? And there's a lot of energy in these evaluation competitions, coupled with the metrics to guide the research. Then when did things become commercial? Because there is in this whole ecosystem a big presence of companies. And then what's an example big system that we all know about? So in speech-to-text system, change speech waves into text strings. In the 1960s, and first people tried with physiology and then machine learning, and I'll show you some details later. There's a word error rate as one of the metrics. NIST is an institute in Washington that does a lot of measures and help to standardize the work. Here is some Covox and AT&T and Dragon systems that you could buy in those times and later. And today you can use Apple's Siri. You can talk to the cell phone, you can talk to Siri, and you can understand, it can understand you. Information retrieval, find the web documents, their recall and precision are the big measures as applied in these evaluation competitions. And today we use Google and Yahoo and Weibo and others like this. If you look at machine translation, translate from one language to another, started very early, from linguistics into machine learning. There's lots of metrics here. DARPA was a big funder in here. DARPA runs evaluation competitions and others too, of course. Systrand is an old system. Today, everybody uses Google Translate, and it works fine. Question answering and summarization. I give you a question, an information need, give me back the answer, a long one or a short one, make it longer and shorter, etc. And there's all kinds of metrics in these different, there's complicated stuff in here, lots of different competitions there. And today, most people know about IBM's Watson that did this television game competition. I would like to look at these 4 and look at what happened here. What kinds of solutions, each one arrow showed old methods and new methods. What happened when the new methods came about? And how can we try to put ourselves in a position with a new center and the forces concentrated here to go and make new solutions that really count? So let's look at speech. In the 1960s, the challenge was, I give you these 9 digits, 0, 1, 2, 3, 4, and I say them, and you must please give me back the spelling of them. Build a computer system. So people looked at the throat and the neck and the tongue, and they tried to build models of these, and they tried to model them in the computer, and then to say, well, when my speech wave has this in this shape, then it's this model and this and stuff, and they tried to get the letters, and the performance was terrible. It was really bad. And then came an interesting step at Carnegie Mellon University in the mid-1970s by Raj Reddy and his colleagues. They made 2 systems that said, forget all this. We're going to make, I'll show you on the next slide how, a machine learning system that learns to cut up the speech wave in little pieces and learns for each combination of little pieces how to convert that little combination into a phonetic unit, and then learns how to combine the phonetic units into spellings. And they had to use this sort of hidden Markov model technology that is a little chain of possibilities like this, and learn the numbers of, do I go this way or this way or this way, what's most possible using machine learning, and then to search through this using algorithms called Viterbi algorithms and expectation maximization and things like this, and moving away from trying to model the linguistic shape, the physiological shape, into some abstract space of representation with machine learning, unlocked this power. Within 2 to 3 years, the whole field revolutionized, and everybody used this technique, and today you can speak to a computer and can understand. The way it works is a sound wave comes in when you speak, and you do something called a Fourier transform that just cuts the sound wave into lots of little pieces and says the very slow wave that happens and the very fast wave, there's so much it happens here and stuff. So if you say the sentence 2 plus 7 is less than 10, then the 2, the plosive of the T, there's nothing, and then suddenly that little wave, that blackness there, that's the T, and then 2, and then P is again a plosive, so there's nothing, and then suddenly the P sound comes out, there's a P, plus there's this that black thing, that's that fricative, that S is black. 7, there's the S of the 7 is less than 10, there's the T again. Some people can actually read these things. When you have this representation, you can now cut little time slices and say, well, okay, for a little millisecond here, I've got this wave, and now I've got this wave, and now I've got this pattern, and this pattern, and this pattern. You can re-represent those patterns inside a space like this through something called cepstral analysis. And you put a lot of little dots here, and you say, I've got this little packet, and it happened for, so many milliseconds. And I've got that little packet, and it happened a little bit longer. And then you can look at these shapes like fingers, and you can say, this is a fingerprint of a S, and a shorter one is just over here, that's a fingerprint of a S, and this is a Ts, and whatever shapes you have here. And when you can recognize, for slicing this up, each little picture like this, you can recognize and put a sound on each of them, and you put the sounds into this kind of a network here, and you say, well, when I have this sound, maybe I go to that sound, or maybe I go to another sound, and you learn the transition probabilities through looking at lots and lots of examples. And you get little phoneme sequences, and then you do another one of this, and you get spelling out. That's how this works. The main point here is the difference from the old representation into this representation plus machine learning. So please remember that. Okay, now let's look at information retrieval. This is the task of finding in a library or on the web the document you want. In the old days, you all remember, if you're older than 30, that you went to the library and you pulled out a little index card, and it had the keywords there, and it tells you where to find books or journals that have these keywords in them. And there's a big work is to make this. And people tried this and tried this and tried this, and then people, Sultan at Cornell University said, forget all this. We'll make something called a vector space, and every document will be its own little position in the vector space, and you put in a few words and it'll locate you in the vector space. He changed the way we think about documents. And then Cleverden in England showed in some experiments that you must just put all the documents, all the words in your document into that vector point, and then you can make it work. And the transformation here was to move away from thinking of a document as a set of words that you have to look and carefully create a special index, into just a little vector of a little dot point in a vector space like this. Each little dot is a document, for instance. And you say, well, here is this word oil and a word fire and a word there, and then some little, I can put my little document here, and I say, well, I have lots of times the, and sometimes index, and sometimes fire, but no times company in this document. And this one has a lot of words of consumer and the, but no words fire, etc., etc. So every document has its position. And when you type in a query for some words, it says, oh, you want this word and you want this word. Look in this part of the space because you want these two words. Oh, there's a lot of documents that are relevant to you. These documents are not relevant to you. And that's how Google gives you the documents that it wants, using something like this. To know how far the documents are, given that you're in a space like this, you can define distance metrics to say how much similar documents are from one another, how many words, the distance between two words. This is the Pythagoras theorem in multiple dimensions. There's lots of different ways you can measure the angle, the size of this triangle here, called the cosine distance. The point is, even if you don't understand the details, the point is the representational shift from thinking of a document as a set of words, you have to read all the words and carefully pull out the keywords and put them in a place, into just a point, a vector with all the words hidden inside that vector, and one quick way of finding this through this vector space technology and this distance metric, that opened up the possibility of doing web search. Let's look at machine translation. In 1950s, the American government, after the Second World War, gave a lot of money to Georgetown University to translate Russian Air Force manuals into English. And they did all kinds of work. And then in 1960, about 5-6 years later, a report came and said, this is nonsense, this work doesn't work. And it killed the whole program in the United States. What they were doing was they were trying to make grammar rules. Chomsky was very important at that time. And they were trying to model the grammar rules in the computer. Then in 1990s, late 1980, early 1990s, a group at IBM produced what they call now statistical machine translation, where they said, forget all these rules. We don't need all these rules. We look at the words on one side, and we look at the corresponding sentence on the other language, and we just find a mapping. This word tends to go to this word, and this word tends to go to these two words, etc. And we just build this big, big, big correspondence table, and then you give me a sentence, I just throw it over through my table, I get my words on my other side, and I just order them roughly what would make a sensible order, and that's how I do my translation. There's the translation model to throw the words into the other language, and the language model to order the words in the new language. And the mathematics that governs this looks like this. It's called the Bayes rule. And they copied some ideas from speech processing using some of the same algorithms, EM and Viterbi search. That transformation was amazing. That unlocked the power to stop doing very careful manual linguistic transformation work and just use big, big, big machine learning on big data, much more than any human being can look at one time. And you ended up with little tables like this that were quite interesting. I don't have time to go through the table. Self-explanatory when you go through if you go through the slides later yourself. Later work showed that the early work on linguistics was not wrong. It was just not using machine learning to the best effect. So current work in machine translation take the basic approach of learning the correspondence between two languages, words, and structures, and then building more and more linguistic type information structures in there, but learning their correspondences too. So the transformation here was saying, let's go away from just pure linguistics immediately, and let's use machine learning as the tool to employ the best kind of linguistics to get the best kind of results. It was a transformation, a leap in transformation that introduced machine learning into the whole methodology. And finally, question answering. In the old days, people looked at questions, they tried to parse the question into a parse tree, they tried to parse the whole possible text answer space into parse trees and do some kind of pattern matching between them. And then IBM came with its Watson system, and they said, you know, we can do this, but let's make it much, much more rigorous and scientific. We broke up over 10,000 little types of answers, one for locations and one for poems and one for rhyming and one for time and one for famous people, etc. And then we go and look at the patterns. We learn the patterns of each type, and we learn the answer expressions for each type. That what does a question look like when you say, who is Nelson Mandela? You don't ask, he is a man. You want to know, why is he famous? It's called a why famous question. So what are the why famous types of sentences? You want to have some kind of accomplishment or a prize or something in that answer, right? And they built a very, very powerful workflow model in which the people at IBM could build their little model, put this into the system, and go for lunch. And 3 hours later, they come back from lunch, and the system has taken all the test data sets and run it with and without this new module and gives them the graphs to say, did you make an improvement or not? It was a phenomenal work of engineering. It was not really a difficult new idea or a complex new representation. It was just good engineering. And that made a big difference too. That was a methodological shift. So here, this just talks about the little patterns and matching the patterns. This graph is interesting. This is from IBM. They gave it to me. This shows the percentage of the answers that the system tried. Here it tried to answer every question. Here it didn't even try to answer anything. Here it sort of answered half of the questions. And this is the correctness of the answers. So in the beginning, it said, well, when I try to answer everything, I'm not so good. I'm only like 15% good. And if I only change the questions that I really am sure about, still I'm less than 50% right, but I only try to answer 3% of the questions. In December of 2007, the line had gone to here. In May of 2008, it had gone to this line. And you can see month by month by month by month how the system got better through just careful engineering until they came up to this blue line here, which was November of 2010. And these little dots are the performance of the best players of this game on television. When they plotted onto here, how many questions did they answer, how correct were they? The red dots are the best player of all time, Ken Jennings. And the system, when it had its big television show, it actually beat this red guy here. It was lucky. You can see the red guy's better mostly than the system. But in this particular game on television, the system made a lucky choice and it won. It should not have won statistically, but it did. And of course, IBM will never play with this system again, because they will surely lose against this Ken Jennings guy. But they did win the one, and that made the news. But you can see through the engineering how the methodology pushed. It was not deep science, it was good engineering. So in each case, these changes had an impact, made a difference, because they changed the representation from an old representation into a new one. They changed the procedure of how you actually work with that representation, and they changed the methodology. They brought in machine learning, they brought in engineering, etc. These three bold-faced words, representation change, procedure change, and methodology change, I think are the secret, are the formula for successful, impactful change. If you bring something new into the whole space of natural language processing and AI that has these three capabilities, these three aspects to it, new, my prediction is you can make a very good impact, a powerful impact. So here, representations today. It's the encoding of words. What is it? It is the encoding of symbols. You can use symbols to encode a word. You can make distribution vectors. You can make embeddings, which we use today, neural network embedding, just an abstract vector of numbers. You can put lexical features on them, so part of speech tags, sentiment tags, etc. You can make groupings of words and represent topics, semantic types, etc. You can build hierarchies of such things like WordNet and so on. These are to represent, these are the tools you use to represent what's inside the text or inside the speech. Now, how you work with them, what's the procedure? Well, you can make special algorithms for particular tasks like CKY parsing to produce parse trees, or Viterbi search to work through a network of options. Or you can make general procedures like aligning two sets of things together, two sets of words, or a lot of machine learning techniques here. Or you can use modules even more general that you can follow, you can pipeline one after the other and train each one and just connect them together like a little series of transformers, finite state machines in the old days, deep neural networks today, etc. These kinds of procedures are what we use. These are what we teach the graduate students how to use. Now, the methodology is often not taught. It is extremely, extremely important. The whole idea of analyzing your problem, abstracting away, finding the appropriate representation and the matching procedure, designing the approach, that is something that we don't formally teach the graduate students. We expect every student to learn and every good researcher to know sort of intuitively. That is, systematizing that is a very important thing, and good researchers know this, and they actually pay a lot of attention about how this works, especially the step of abstraction. Now, we use a lot of data, of course, because we have to test that our things are correct, and so people have to give us the results that the machine must copy. So the whole science of how you put the information into the text, how you ask humans to put their notation on top of the text for data and to drive our own understanding is really an important step. I believe in our field this doesn't have enough attention there. And of course, the whole IBM-like training and testing cycle around and around, getting better and better in all these facets. These are three important facets, I believe, of NLP work that we have to foster and we pay attention to if we want to do good research. So we get a cycle like this. Given a new problem, first you do your analysis, your theorizing, your annotation, and then you get procedure and you learn how to do the transformations from what you got to what you want. And that's sort of a representation type step, putting the machine learning to make the representations happen. And then you say, okay, now I can do it. Now I want to do it big, large scale. I want to go and make a company. I want to make Google. I want to make $1 million. I want to make a QA system and sell my company. So you focus on the procedure and you make it large, powerful procedures, often just making very large tables of options, not very deep, intelligent visualization, just remembering everything. A lot of machine translation works this way. And then you run into some problems and you say, some things I cannot do. I just cannot do. You find those problems, you try to then go back to the theory and say, why, what is going on here? And maybe you need to change the methodology of how you're looking at the problem, how you're approaching it, what you have to sort of apply. These 3 points actually apply to everything, but they sort of focus on these 3 arrows here. So this is a cycle we do, and in the middle you test. Of course, you test everything you do, always, all the time, to make it get better. The kinds of people who play a role here at the top are often linguists and cognitive linguists and researchers. The kind of people who play a role here are most NLP researchers today, a lot of machine learning experts, etc. And the kind of people here are very much company engineers and big data type people here. And we work together, all of us, to make this field work. This field is not a simple, uniform, tiny little area. It's actually a complex interrelationship between these different kinds of attitudes, and different people gravitate toward different kinds of work. People who want to make money and like engineering sit here. People who like algorithms and like programming sit here. People who like language and wonder about theory sit here. But they talk to one another in this fruitful cycle, and we have therefore an interesting space in which you can, through your career, through your life, play in different fields, and you constantly learn from one another. That's, I think, what makes our field so dynamic and exciting to be in. Now, within this field, you make changes all the time. That's what you do. And then you publish your changes. But many changes, most changes just don't matter. It's not important. Yes, you can have various kinds of part of speech tags and shallow semantic tags, and you can have lots and lots of kinds of grammars. There are lots of dozens of kinds of grammars. You can have all kinds of senses of words. Is it 2 senses or 5 senses? You can have different kinds of distribution of word vectors. These are good. These are good to investigate. There's always some kind of vocabulary of features. Exploring them and having different options may give you 2% better here and 2% worse there, and so on. For me, really, it doesn't matter. I really don't care. If there's a big representational shift, then you will hear about it, and it will change everything here. The same with the procedures. There was unification in the old days of taking various kinds of information together and matching them together and carrying the matches to the other side. There's various kinds of parsing, many parsing algorithms, hundreds of, over 300 clustering algorithms in one book I saw, lots of grouping and clustering results, topic models and things like this, very many kinds of machine learning algorithms of different kinds. And yes, it's important to investigate this. Yes, graduate students are super happy when they make something new here. They think they've changed the world. Unfortunately, they haven't. They've just made another variation in space. Now, experimental methodologies, that's harder to talk about, but the idea of ranking and re-ranking, for instance, is one that will come and they say, re-ranking, oh, that's different from ranking, so it's important. Yeah, it's not really so different, is it? Annotation by experts versus types of crowdsourcing. Yes, it's important to explore what's the level of training of your annotator, etc. These changes are all important to research. They do make improvements, but they don't make fundamental changes in the way we do our work. What I'm interested in is those magic fundamental changes. I want to find the transformation points. I want to find those points that give me a new representational paradigm. Like we used to have a few exact manually built rules, and now we have many learned quasi-rules or transformations in some kind of transformation table, and sometimes the transformation table is in fact a neural network, right? But the neural network today is at the same time a procedural paradigm from a series of modules that delicately give you change, give you the result, one good result in the old days, to today a kind of series of modules that give you multiple results ranked and maybe captures the representation inside of it and merges these two in the neural network paradigm. And maybe, if you're lucky, a new experimental methodology that takes, instead of a subtype after subtype after subtype of the problem, now I'm doing biomedicine, and then I'm doing engineering, and then I'm doing legal text and stuff. Maybe I can just have one new methodology that captures all of these in the same paradigm, in the same way, and gets a general answer for them. So if you can find changes along all three of these dimensions that really work, then you have a chance to revolutionize the field. Now, sitting here looking at the slide, you say, that's impossible. Who can possibly do something like that? And I ask you to remember the beginning of the talk. The speech guys did it when they started putting hidden Markov models and machine learning away from the throat. And the information retrieval guys did it when they brought a vector space away from just document by document, little word collection, things like this. And the machine translation guys did it when they brought machine learning into associating words. It is possible to do, to look at the problem we have in a completely new way. And I'll give you two new problems at the end of the talk that we need ways for looking at that could revolutionize everything we do. So let's look at this here. In the 1950s, people tried anything. Then came the features in state space and finite state machines around parsing in 1960s. And then came the vector space, the distance, the clustering metrics, and the evaluation that I told you about in information retrieval there, coupled with this evaluation often run by the TREC competitions at NIST in Washington. About 10 years later, a little bit before, came the finite state machines in speech recognition with testing and training. And a little bit later there came probabilities in machine translation, as I told you, with expectation maximization of Viterbi search to do the statistical new kind of machine translation. A sort of annotation came at the same time and grew at the same time and kept going. In the 2005, sort of in those 10 years, people were exploring machine learning, finding latent dimensions, finding latent topics and so on, and different kinds of groupings and what you can do with them. I don't see any big revolutionary step there in that sort of decade. But a few years ago, deep neural networks came with embeddings, and they revolutionized everything again. I think everybody will agree this is a big step for us all here. And now the question is, here we are 5 years later. Are we due for something new? What would that be? Could we do it? When is the next big new thing coming? Because clearly it's going to come. And where will it sit? How will we prepare our minds to recognize it when we see it, so that we can start, working on it early as possible. So this is a good roadmap, I think, for us to have. So here at this point is kind of the middle. I'm sort of asking you, well, where are we going next? What is your input for these three things? Good question, huh? Interesting question. So let's look at where is NLP headed, and then what does this mean? Now we go quickly to the end. So here's the summary. Trying anything, using theories, but slowly moving into non-theoretical machine learning techniques. Machine learning wins there. Deep neural networks reset the clock. And overall, I think vector spaces are the big invention, that you can put words or documents into a single dot in a vector space with a continuous distance metric. And now you can handle millions of items in the same way, in the same space, scale invariant, words, documents, topics, it's all the same in the same kind of space. And then for transformations, hidden Markov models and Viterbi search there, you can handle complex transformation sequences. And then machine learning algorithms, many of them, and now we have the neural networks here, and we sort of get to a more uniform approach. Doesn't matter what the particular problem is, we put a representation into a vector space and we do a transformation that we learn. Right? That's sort of what we now do. This is our state. So this summarizes these things. We started with symbols, we had vectors for representation, and now we use embeddings, but we don't understand what the embeddings mean. Procedures, we had manual algorithms, then we had variations of machine learning algorithms, and today we use deep neural networks that can learn anything. We just give them the data, but we don't know how they do it. The methodology, we tried to implement linguistic theory, and then we had data annotation things, and now we just give the neural networks the input and output, and we say learn, or we give them something in the middle, and we don't really know what we should give them to learn for maximum effect. So while we get better at doing the engineering, we retreat. less about how the actual engine works. So we become more abstract, but less understandable. We're more general, we run on any input, we're more numeric, we're more scientific, we can measure things and things, less language oriented, but we're always less interpretable, less explainable, and we have to focus on this part if we want to make good progress in the future. So here's the two futures, I think. All our applications in language, we reach a plateau. For IR, open domain, speech recognition, information extraction, everybody reaches the top. And then you put in something new like neural networks and you push it up by 10% on average, but you still reach the top. You still cannot get better. What's going to break these barriers? What's going to make things go better? How can we do that? Well, I think we need to look in these two places to break the barriers. People, look at people. When people don't know something, they don't just sit there and sort of try to read again and again the same sentence. They talk, they ask one another, they go to the web, they say, what's going on here? Help me. So there's something about interaction and teaching and giving knowledge that we need guided search and interpretation of knowledge and recognizing when we don't know something and recognizing how to ask for it. And then, given that something comes in, we can reason with it. We use knowledge. We don't just sit and look at the language. We internalize and apply reasoning and inference. These two, dialogue and knowledge representation and reasoning, these are the areas I think that our field is moving toward. So we're going up and down. Up from text alone to interaction, which involves dialogue strategies, speech acts, initiative, obligation, intention, etc. Partner models, interpersonal pragmatics, style, emotion, all that stuff. Other media, non-standard language, tweets and funny spelling and emoticons and all interruptions, all this inside the space here. These are things that we all know, and we know they're relevant. There are areas in natural language processing that deal with them, but they have not yet come together in one uniform, single methodology application area. That's, I think, a place that we can go working on. And if we can find the same sort of transformational paradigmatic shift, we can make a big push here, and we can give people something more better than Alexa and all these stupid little systems that sort of are boring, something that's more interesting and that works better. But not only down, we can go up. We can go down into knowledge and getting better knowledge representations, getting systems that learn their own representations and then learn what they know and what they don't know, and know how to go and find out about what they don't know and grow their own knowledge and understand what's sure and what's possible sure and what's still under question and stuff. The exact things that we do, that children do. Make a hypothesis, test it, ask people. Our systems don't do that. Certainly our language systems don't do that. And the knowledge representation systems are so far away from this, they don't even know how to think these questions. We have to bring language and knowledge representation together to do this kind of work. To do knowledge work about content learning, content organization, and reasoning work with inference, rule creation, and usage. And there is already some natural language work in this space, but again, it hasn't gelled. There isn't a single methodology, a single approach. We don't know how to measure things here yet. Okay? So to be significant changes, we need representation, procedure, and methodology at the same time, a shift. So we need, for representation, something about the system's goals. I know I don't know something and I want to know it, so I need to go read about it. I'm hungry for knowledge. I don't know any NLP system or AI system that is hungry for knowledge and will tell me where it wants to read and how much effort it's going to make to read. I don't know any that can do good cross-medium representation from text to image to video to speech, although we're starting to make good progress on that. I don't know very few that do partner models about what will a partner like and accept and why must I do work like this, etc. In procedures, yes, neural networks, algorithms can do wonderful things, but we don't know how they work. We need to be able to understand and debug and explain them and know when they make a mistake how to fix that. And for the methodology, we have to somehow be able to begin to measure the external knowledge, the knowledge in the system, that how to measure, how to quantify knowledge correctness, how to measure external knowledge and say, is this worth reading or is that worth reading? Not only fake news and judging if something is fake or not, although that fits there, but much deeper and more powerful methods of measurement of knowledge. So it's these three things together we have to bring our thoughts to. So I have 2 projects that I think will matter. So we're almost finished, and then we can have a discussion point. 2 projects that matter. I propose. One is interactive multimedia summary report writing in partnership with a human and a machine. I give you a bunch of text that describe my project or something. I give you all the papers that I've done in the last 6 months, and I say, please help me write the report for my funder and for my boss. So I can make it a little template for the structure for this, and then the human can sort of say, well, in section 1, I want 3 sections, and section 1 is going to be called this, and the machine says, oh, this is section 1. Let me go find pieces of content automatically and put them in section 1. And it puts little fragments there, and the human says, oh, that's good. No, this fits in section 3, and this I don't want. And then the machine and the human together write this report, write the summary, such that it can be tailored. It can be a long one and a short one, a high-level one, a detailed one. The human can drive it, and the system has to follow, and the system, crucially, has to learn. So how do you evaluate this? How well can the partnership tailor the output to different levels of knowledge, different levels of interest, short or long, etc., etc. Task in multiple media. Take in multiple. There's a spelling error. That's one interesting task that involves a lot of the dialogue capabilities, but it begins to be measurable, right? The other task is the down one, is looking and saying, now I want to go look at knowledge. Let me build a machine that is reading to learn. A lot of people have tried this, but what they mean is sort of open domain, open information extraction and things like this. And they take little facts. They say, well, here's a set of little facts I put together in a simple little frame. And the frame sits in a big knowledge, in a big sort of list of frames or a big structure there. It's not organized. It doesn't generalize into some kind of memory structure, some kind of case-based reasoning kind of organization. There's no inference you can do off that except answer simple questions. Nell tries to learn little hierarchies of terms there, and it cannot do so for anything except simple noun types. Kairos tries to learn little event sequences, the Kairos programs there. We don't know how to target our knowledge output, how to organize, what types of knowledge we want to learn, and how to organize them, and how to focus the system on places where it says, here, I have a mess. I want to go read about this to fix my mess. I need to learn about this facet. When you do your studies, you know the place where you have trouble, and you go fix it. You ask your teacher, or you go and ask the web or something. No system we have today can do that. It doesn't know to measure the entropy of choices at a point of the representational uncertainty or something like that. We have to build systems that do that. Not only at the content level, but also to learn their inferences, to learn how they can work with their knowledge to fix their knowledge. Some people will say this isn't NLP anymore. I will respond, NLP and knowledge are the same thing. Language is the outward face of knowledge. Knowledge is the inward face of language. Those two are married. You cannot cut them apart. We cut ourselves short if we ignore the power that we get from working inside knowledge space. So what does all this mean for HITS? How can HITS go and make significant changes and move from I don't know, from Neanderthal to human or something like that? Right? Where are we? I think a birth of a new center like we have here is a change in the world that is significant for our world, our little world of maximally 50,000 people. And it is something that all NLP internationally can be happy about. When so many good people can focus in one place and can find a home and can work together to think about these questions and maybe to make the breakthrough. The breakthroughs do not happen unless you have these centers. If you look at where these breakthroughs happen, they always happened at a center like HITS, led by people who are dedicated, who love what they do, who are good. HITS has exactly the right formula to make this sort of change happen. It has strong and deep experience, very high quality researchers and very high quality research. You saw the numbers that Eneko said earlier. Deep international connections, so you can draw on people and go and visit people and ask questions where you don't know and come back. Imaginative and open leadership to new problems. There are some centers I know of where people say, we do, I don't know, phrase structure, grammar like Chomsky, and we will never do anything else. And you look and you say, excuse me, that doesn't work. And they say, don't tell us what doesn't work. That's what we do. HITS is not like that. HITS is pragmatic and open to new problems, but in a way. The dedicated leadership, I would like to call out Arantxa, Ilarraza, Eneko, and Germán. These three people as people who have done a phenomenal amount of work to make this center come about. Of course, there are others. Forgive me for not mentioning everybody. Of course, there are politicians, there's money, there's all the stuff involved. But it has to focus around some people who put their heart inside and stand there when the wind is blowing and things are difficult, and they say, I have to do this. And these three people are three of those people that are the pillars of HITS. I respect them, I welcome them, I salute them, and I hope that HITS will have a fantastic success. It's poised to take on a leadership role and make changes that matter. Zorionak.
Thank you very much. Thank you very much. Yeah. Well, I'm astonished. So thank you. Now it's we have a few time for questions if you want. Also, if you want, I think you can also make comments in the chat. So if you have any question, please let me know. I have some comments and questions maybe. And I don't know, also Eneko may have some questions. I don't know.
Germán, maybe.
Yep.
Sorry, Germán. Maybe you can mention that people can take the mic if they raise their hand, which is a small logo in the bottom. They can raise their hand and make a question. Or they can chat.
Yeah, also chat, but also if you want to say something, if somebody wants to say anything, there is a raise hand button at the bottom. Yeah, you can raise your hand, and then we can give you access to. So yeah, Klaus, let me see if I can see you. Fine, Klaus. Yep. And
I see Thierry has his hand also.
Yeah. Sorry, wait a minute. I don't know if I can make you. Like you can make you can make presenter. Okay. So I don't know if I can make you a presenter now, but you can make the question with the chat, I think, because this is the special platform now for so many people, and then it's not allowed to make you present or you make the question. So sorry about that. I make participant maybe. Yeah, you can. I think you can say something, Klaus. No, Klaus. No, sorry about that. I think you can make the question, please, by chat, or even though it's not allowed. Maybe I don't know. Sorry about this, Klaus.
So maybe in the meantime, while Germán tries to give the voice to Klaus and other people making a question. Well, thank you very much, Ed, for an inspiring talk. It's really great that you have this general view of the field, and reminds me of the important role that we have of just not producing papers after papers of incremental work, but thinking on where we want to go. So you mentioned reasoning as one of the key ideas for the future, and I agree, but also I have to admit that I kind of see reasoning, because when I learned natural language processing, reasoning was one of the main tools that we were routinely using to build representations. But I kind of feel that maybe because I was there many years ago, I don't see fresh ideas in the reasoning field. So I wish somebody will say, okay, I have these ideas about how to implement reasoning and how to maybe do reasoning with backpropagation, or there was this talk about doing differentiable programming, but in the end, I don't see new ideas around. So, do you have any suggestion, or do you hear about somebody else who has kind of not a solution, because this is a really hard problem, but like suggestions of which could be the direction that the reasoning could go?
So Eneko, this is one of the questions that exercises me the most in all the work I do. It's like, if we think of reasoning in the old paradigm of, I have some situations, some facts, I have some reasoning rules, I map the reasoning rules into this, and I make new representations because they generate out the new representations. It's just an information transformation, like anything else, like doing tagging of various kinds. So if you think of it in the old paradigm, you think, I have to go and learn reasoning rules, and I have to build my representation, and people get stuck. The knowledge representation community has built this kind of thing for decades, and they've come into a space through the semantic web, when they all moved away from KR and R into the semantic web, where they don't do the formal, difficult kind of proof type reasoning that Levesque and others do in the early days of KR. They do sort of RDF hacking and big data hacking and things like this. But that's not what we need, right? The methodology, what we need is a new way of capturing the knowledge and capturing the transformation and learning the reasoning transformation in a way that's sort of natural and easy, like our new paradigms for vector search or for IR or for machine translation. So now, naturally, one thinks of deep neural networks, where you say the knowledge and the transformation are in one engine, they're together. I learn the embeddings, and I learn the transformations at the same time. I just give my input-output pair. And you say, okay, I know from my methodology in NLP, I put Spanish and I put English. I put question, I put answer. I put something there. But when I'm moving into reasoning space, I don't have a corpus to say, here's representations 1 and here's representations to learn the inference, build the representations of this. All we have is some kind of weak graph convolutional neural networks that take graphs and try to create an embedding that represents a graph structure. That's a beginning. But I think we have to design a problem and a methodology and a representation, those 3 things. We have to design them in such a way that we can build some kind of knowledge. We must move into the knowledge space and build some kind of representations where we don't necessarily work at the surface form. We work one step in on the knowledge form, and we teach the machine to do the knowledge transformations and learn its inferences and learn what to do under which conditions. If you say it that way, it makes it sound impossible, because then we have to design knowledge representation languages that do the big thing and take AMR and other things and use them. That's the simplistic way of doing it. Maybe that's correct. But maybe we can say, okay, we know we want to work on the knowledge on the inside, but we have easily accessible the language on the outside. Let's see if we can do 2 stages, hop from language into knowledge space, and do something where we train the machine, we guide it through adversarial training or something to make its own knowledge representation, and then we learn the transformations, the inferences from that. So that's the best of my thinking, is how to force the machine to build its knowledge representation level, not just simple embeddings that look at word contexts as the embedding, the source of the embedding structure, but that look at knowledge as the source of the embedding structure, and then do the transformations across the knowledge. If I knew how to do that, I would do that tomorrow. And I have a feeling that all of us, if we knew how to do that, would just jump on it and do it. It would become a natural thing. But that's the magic little trick. I don't know how to do it. I wish I did, because then I could make the same magical change that we all hunger for. And I think you guys, for instance, at HITS, there is only about 10, 12 places in the world that I would think of when I think, who could make this kind of leap? who could think these thoughts and make this methodological and representational shift. And you guys are one of those 12 faces. So I wish, I sit here and I wish that somebody will do it and show us the next big talk and the next paper, because then half the field will go into the knowledge, language plus knowledge space tomorrow. And we will have unlocked a new level.
Thank you.
Thank you very much.
I
have other questions, but I think it's better that other people have questions. Thank you.
Maybe Klaus, yeah?
Can you hear me? Yeah, hi Ed. Thanks for your really inspiring talk. I'm actually a former CMU PhD, you may know.
Ries? You're Klaus Ries?
Klaus Seckner. The other Klaus Seckner.
Oh, great. Another Klaus. Okay, sorry, Klaus.
Yeah. So in any way, morning, because you know, when Hinton and others came up about 10 years with this new paradigm of thin air, they used the same, and Hinton was involved 30 years earlier, you know, in deep learning work, not deep learning, but neural network processing work. They used the same structure more or less, but they built it in a more multi-layer way, and what they had was processing power, computing power, larger data sets, and better training algorithms. So I wonder if it's sometimes not just the intellectual thing, you know, that you come up with a new algorithm, which maybe is just you pick up something that's already there, but with the improved technology, with a larger amount of data and some other ingredients, you make it into a transformative paradigm.
Yeah, that is correct. That is exactly correct. And we don't know if the solution requires bigger machinery and more data than we have today. You know, we don't know it until we see the solution, and then we'll see, oh, we had to have the bigger data. The same was true for machine translation, and in the SMT paradigm, 10 years earlier, it couldn't have been done, right? So it may be the case that if we want to do the knowledge revolution or the dialogue revolution, we have to wait. My private opinion is that we have enough compute power and we have enough data, or we can get enough data for both of those in certain limited kinds of domains. We're very, very good in our field at limiting the domain, and we've learned that lesson. So I do believe that if somebody has a powerful revolutionary conception of representation and methodology and procedure change in either of those or another area, I believe they'll be able to pull it off in neural network space. What I don't like about neural networks is they're so over-engineered and they're so big in their representation power that essentially for many problems they just become a big table. It's just a lookup table. And so what I like the best is the experiments where people try to make their neural network as small as possible, as low as possible, and to say, now my network is saturated, its information representation transformation capability, its power is sort of optimally used. And now I have a sense of the sort of information theoretic, information transfer size in the information bottleneck type sense, the mutual information cross entropy size of the problem. If we look at that kind of work, I think you see that we have most of our problems are much smaller than the networks that we tend to use today. And so I think we have in even our current computational environment and machinery much, much, much more power than we really use. So I believe we can go quite confidently into bigger problems and we will still be able to handle them. It's a long answer. I don't have the truth, but that's my hunch.
Thanks.
I mean, it's a problem, right, for us, the deep neural networks. If I give you a motor car and I say, you know, this car is great, it looks beautiful, and it's so easy to drive, and it can go 150 miles an hour, no problem, but sometimes it's going to go left when you want to go right. And sometimes it's just going to stop when you want to go. And I don't know how to control it. In fact, I don't know why it does that. But usually it's good. Will you trust that car? Will you buy that car? No,
No.
we're sitting in a bit of situation. That's our problem.
I think now, well, I'm sorry about that, but I think the configuration here is doesn't allow to make the chat. So if you want to participate, just raise your hand. So now I think it's the turn of Thierry. Thierry, do you want to participate?
Yes, sure, thank you. First of all, Ed, very nice to see you again.
Yes,
and even much nicer to hear to your talk. So it was really a very nice overview of past and present, and an opening to possible futures. So my question was that it's more on the side of the down level, so the knowledge and not the dialogue, but the creation of a language term or neologism are all in the context of interaction between human and real world historical facts and social facts. We had this with the Brexit, this new word. So this was created about this decision of the Great Britain to leave the European Union. And now in the COVID time, there's a lot of, and this seems to be in the interaction between, let's say, the real world and the language and us as cognitive generator. So do you see there a possibility to join a representation of those historical, social, and whatever, and the language? Because most of the time the knowledge we consult is a posteriori. I mean, it has to be written by someone, it has to be included in taxonomy, ontology, thesaurus. So this aspect of innovation, let's say creativity in language. That's it.
I think thank you. I think that's a really interesting question, because the nature of our psychosocial environment as humans is reflected in the language we use. Certain words we use and then suddenly we don't use them anymore because it has become socially unacceptable or something. Or we say, I am a European, and suddenly we say, no, I'm a British subject or something like that. Certain shifts happen, and those shifts are reflected in the language and can be picked up by even current day NLP technology. The things that happen behind them, the bigger causal forces and the bigger sort of psychosocial, psychological and social structures that govern those choices, I think those are probably hidden, right? Those will be very hard for machines to induce, our current power level of machinery to induce. But to find the aggregate shifts, to notice that in the discourse inside England, suddenly there's this word Brexit and a whole bunch of associated terms becomes really popular. And the same inside France. And the sentiment connotations around this nexus differs in these two countries. You know, any system, even today's sentiment and LDA type systems can do that. And they can pick up and say, there's something called Brexit with these words and something called Brexit with these words. And in this side, it's popular, and this side it's negative, and this, and there's a bunch of disinformation about it. And there's certain groups of people who tend to say they like it or they dislike it, and they have higher vocabularies or lower vocabularies, etc. I believe there's a lot of this kind of profiling, psychosocial profiling, that already in our community we're starting to do, as you know, right? People are starting to do this. And the more we do this, the more we build the stepping stones and the building blocks toward these bigger structures that we would eventually be able to recognize historically as reflecting something like Brexit or something like COVID or something like whatever challenges our societies face. But as you say, it is, of course, backward facing. It always looks at the language that has been written. It cannot predict things forward facing. We're not doing AI in that sense. We really are doing language technology, working with language.
Yes. Okay. Yeah. This is a good point.
Yeah.
So this is some work for Herman.
Thank you. So yeah, well, I think we are running out of time, but I still have, if nobody else wants to participate, I have a comments or questions also. I think your talk has been very inspiring, as always, and interesting. Thank you very much. But yeah, I think I will summarize a little bit my question and comment is we are a very small group of people, around 50,000, you say, in the world that are influencing this very much, because also it's a group of people maybe that is providing technology, and now even more with the powerful deep learning things which are approaching the technology to the user so very much, and we are influenced. We are every day using NLP everywhere, and even now here, because they clarify the voice, I think, and also all this the noise also of the recording, etc. But I think now it's in some sense this is the NLP time, no? In some sense, it's the artificial intelligence, but also the NLP time, and this is very good. But still, as you say, there is much to be done, no? About knowledge and the connections between knowledge and language, and also reasoning thing. So for me, I would like to have this human machine that helps me to make the reports after a project. So I will buy this. I don't know how much it could cost, but I will like to have this. Well, just one question. I think we still need common sense. So in the NLP, we need, and also explainable things. It has been already there here. Maybe what do you think could be you didn't mention the role of reinforcement learning, because we are not using so much in our methodology the reinforcement learning thing. So, and we don't know how much to do that.
Yeah, that's right. We don't know how much to do that. I have twins, 6-year-old twins now. I look at them and I look at how they learn, and reinforcement learning is sometimes, as anybody who has children knows, very important. You have to say the same thing 16 times before they listen. And other times, you do it one time, and it goes in, and you never have to say it again. And so humans are able to assign an importance to what they learn and to pay attention to it and incorporate it and so on at one exposure, if it has the necessary emotional sort of impact to it. So our machines have no emotional landscape, no emotional topology. They just do the same thing the same way. So if you say, well, why? What is it that people do that allows them to rank the importance of a lesson and to completely override everything else they've heard before from this one exposure? What is the extra magic that makes that happen, that completely destroys the old stuff and just the new? Why do we not try to model that? Why do we not try to think about that? How could I build that capability into my learning system? So reinforcement learning is just saying, well, okay, I give you more example. It's following the old paradigm. Doing something about a graded, differentiated learning system where there's extra force added through some external reasons is a different kind of a paradigm. So I think it will fit into the whole reinforcement framework later on. It will be like a super reinforcement, but in one shot or something. You can cast it that way. But one has to think, I think, at this level and think why. So sure, yes, we must do reinforcement learning, and we must find out different ways of optimizing and things like this. But at the extreme, it's more than current day thinking. What that is, I don't know. Right? Again,
well,
come to these points. Yeah,
a lot of things to do to continue doing. I think a lot of work for us in the EAT Center and also in any other place where people is interested on NLP and language technologies. So, well, I think we are going to finish because we are out of the time. So thank you all for participating here. I don't know if somebody wants to say, Eneko, do you want to say something at the end?
No, just thank everybody for attending this seminar. I would like to mention that we are planning to make this into a monthly seminar. It will be difficult to find such interesting talks every month, but we'll do an effort. And so anybody interested, just let us know, and we will announce the seminars in due time. And
just
and
invite,
thanks,
just,
Ed, for your
just
talk.
invite Ed every month.
Okay, okay. Ed, would you like to do that?
I have some more talks I would love to share.
Sorry, Ed, sorry, bad joke. Ich mach's nicht wieder.
Okay.
Okay.
So thank you again, Ed. Thank you everybody for participating, and we will let you know when we are going to have a new seminar, a new webinar, and thank you everybody. So we are very happy for the new center. I'm very happy also for having you here, Ed. And thank you everybody. Sorry for the chat thing. In this configuration for so many people, the chat is not allowed. So sorry about that. And thank you very much. And I hope to see you all sometime in the future, very soon. So thank you again, and thank you again, Ed. It has been a pleasure.
Okay. Bye,
Bye
Ed.
bye. Bye
Bye-bye.
bye.
So